Now let's look at what H.264 actually is. It's a standard for video compression in the same way that Motion JPEG and MPEG-4 Part 2 is. It's actually designated also as MPEG-4 Part 10, which shows its heritage as part of the MPEG-4 family. It's also known as AVC, for Advanced Video Coding. Developed jointly by the ITU, Video Coding Experts Group, and in combination with the ISO IEC Moving Picture Expert Group. It was actually completed as a first draft back in May 2003, so it's been with us a little period of time now. And the aims of H.264 were to provide a standard which was capable of providing good quality video but at reduced bit rates compared with previous standards, and the intention was to actually achieve half the bit rate for the same quality level compared to MPEG-2, H.263 or MPEG-4 Part 2, which is the common use of MPEG-4 that we're familiar with these days. And another intended objective was to actually achieve that level of reduced bandwidth without increasing substantially the complexity of the design, because that would actually impede its ability to be implemented. It would either add cost or mean that the processing power required would make it such that it couldn't be deployed in a wide variety of applications, and we wanted it to be a general purpose standard. Now let's look at the primary coding tools within H.264 to see how it achieves its levels of claimed compression. First of all, it's interesting to note that H.264 is based on the same fundamental technology that's been with us with all of the major video standards, H.261 right through to MPEG-4 Part 2, and they're all based upon a motion compensation scheme using discrete cosine transform algorithms. Each picture is actually broken into macro blocks, 16 by 16 samples with corresponding colour samples, and they're arranged into slices. And each macro block can be divided into sub-macro blocks to achieve higher levels of accuracy in our motion compensation. We see where say a 4 by 4 pixel block is going and use that as a separate entity. That compares with other standards where we were more or less fixed to either a 16 by 16 pixel or an 8 by 8 pixel block in terms of motion prediction, and so therefore being able to break the picture down in H.264 into those a greater range of sub-macro block sizes gives us improved accuracy in our motion compensation, but at a processing cost. One other innovation that comes with H.264 is the inclusion of an in-loop deblocking filter. As you see in the picture at the top there, then you can notice a blockiness within the picture, particularly when images are highly compressed using discrete cosine. Then there's no allowance made for the boundary between macro blocks. There's no smoothing of boundaries by matching the coefficients of one macro block with that of another in terms of its luma and chroma values. With a deblocking filter, then the coefficients of one macro block's individual pixels are adjusted to match the values in adjacent macro blocks to actually smooth those boundaries between macro blocks. It's important to recognise as well that H.264 was designed to be a flexible standard capable of meeting the needs of many separate application needs, from high quality entertainment systems to real-time video conferencing. In the area of high bandwidth, where we're generating high bandwidth signals very often for high definition images, then to actually get the levels of compression we would probably need to use the more complex compression algorithm tools. So we'll be using very small macro blocks to actually provide the level of compression, and that means that we're going to be doing an awful lot of computation, which takes time and therefore will add latency. It'll add time delays within the system. We can use non-real-time software during the encoding process and use all of the coding tools within the H.264 armory to give high levels of compression of that video. In the lower bandwidth scenarios, typically below a megabit per second, then they're probably going to be low latency because we'll be using real-time encoding, but that will mean that we'll achieve far lower levels of video compression as a result, because we aren't using the full suite of tools at our disposal, because we need to achieve things in real time. Also, it's important to note that any given standard, MPEG-4 or MPEG-4 Part 10, H.264, it doesn't guarantee a level of quality. It purely depends on how the individual standard has been implemented, and the H.264 standard itself really only concerns itself with the decoding process, and then it's up to the individual implementers of that to actually produce an encoded stream that has the level of quality to be compliant with the H.264 standard. That then leads us on to the concept of profiles within H.264, and this is how this level of flexibility is actually provided. So the standard itself provides 7 sets of capabilities referred to as profiles, and these profiles were designed to fulfill the needs of specific application areas. So they can be viewed as feature sets, tools from the H.264 compression toolbox, which fulfills requirements and meets the needs of the application. The initial work on H.264 standards gave us baseline, main and extended profiles, and that was then further enhanced a short period of time later with the frequency range extensions for high definition and high quality applications. Now let's look at some of those profiles in more detail, starting with the baseline profile. This was primarily designed to meet the needs of the lower cost applications for video compression, and it's likely therefore we'll have limited computing resources available to perform our encode and decode functions. Also, it was designed with minimum complexity, recognizing there is going to be limited computing resource available. Then we don't use the higher order compression tools, but what we do achieve with baseline profiles are improved levels of error checking and the ability to deal with a broader range of network environments where we might have fairly high data error rates and so on. Because we are using the lower order tools for baseline profile, that has two effects. First of all, it allows us to provide low latency because we're not using the high levels of coding tool. But also, saying that, we don't achieve the very high levels of compression that H.264 can achieve, and on typical tests you actually achieve round about the 20 to 30% data reduction compared with, say, MPEG-4 Part 2. Obviously MPEG-4 Part 2 and H.264 will be achieving much higher levels of compression compared to, say, Motion JPEG. But the important point to note there is that with baseline profile you're only really in the real world environment achieving about 20 to 30% data reduction, so not a huge amount compared with MPEG-4 Part 2. Baseline profile is very widely used and being adopted in a more wide arena in those of video conferencing and particularly mobile applications. So video conferencing where we need low cost and low latency, mobile applications where network robustness is vital. It's also the profile that's most widely used within CCTV applications, again driven from the fact that we need CCTV to be real-time or very near real-time, so we can't tolerate high latency. Also, the encoding must be done typically in camera or in encoder in a CCTV system, and therefore that's going to limit the processing power available at the camera.